Picture a Roman shipbuilder carefully fitting together a massive wooden hull like a three-dimensional jigsaw puzzle, creating a vessel stronger than anything we build today, all without using a single nail or frame. So sit back, grab a cup of tea, and get ready to discover how Romans built their ships completely backwards from modern methods. We'll explore the ingenious mortise and tenon joints that held their vessels together like interlocking wooden fingers, understand why this shell-first technique created ships that could survive storms that would snap modern hulls, and learn how this revolutionary method dominated Mediterranean shipbuilding for over 1,000 years. In the bustling shipyard of Ostia, Rome's primary port, a master shipwright named Marcus Flavius supervised the construction of a merchant vessel in the year 150 CE. Unlike modern shipbuilders who start with a skeleton of frames and ribs, Marcus began with nothing but a solid oak keel laid on wooden blocks. What happened next would seem impossible to today's naval architects. He built the entire hull shell, plank by plank, before inserting a single frame. This wasn't primitive construction, but sophisticated engineering that produced ships of extraordinary strength and durability. The technique Marcus employed, shell-first construction using mortise and tenon joinery, represented the culmination of thousands of years of Mediterranean shipbuilding tradition. Where modern ships rely on their internal framework for strength, Roman vessels derived their integrity from the shell itself, with each plank locked to its neighbours through hundreds of precisely cut joints. Think of it as the difference between a house of cards held up by external supports versus a solid wooden puzzle where each piece strengthens the whole. To understand why Romans built ships this way, we must first grasp what made their method so radically different from modern shipbuilding. Today's ships are built frame first. We construct a skeleton of ribs and frames, then attach the hull planking to this framework. The planks merely form a watertight skin. The frames provide all the structural strength. It's like building a house by erecting the frame first, then adding the walls. Roman shipbuilders worked in reverse. They built the outer shell first, edge-joining planks to create a strong, self-supporting hull. Only after completing this shell did they insert frames for additional support. The mortise and tenon joints, rectangular slots cut into plank edges with corresponding projecting pieces that fit together like puzzle pieces, created a hull where the primary strength came from the continuous wood grain running along the ship's length. The mortise and tenon joint itself deserves detailed examination. A mortise is a rectangular cavity cut into the edge of a plank. The tenon is a corresponding rectangular projection that fits precisely into this cavity. Roman shipwrights cut these joints every few inches along each plank edge, creating hundreds or even thousands of connection points in a single vessel. Small wooden pegs, driven through both mortise and tenon, locked each joint permanently in place. The precision required for these joints astounds modern woodworkers. Each mortise had to be cut to exact dimensions, typically about 2 inches long, half an inch wide, and an inch deep. The corresponding tenon needed to fit snugly but not so tightly that it would split the wood when driven home. Too loose, and the joint would work itself apart under stress. Too tight, and assembly became impossible. Roman shipwrights achieved tolerances of fractions of an inch using only hand tools. Archaeological evidence reveals the sophistication of Roman joinery techniques. The Kyrenia ship, a Greek merchant vessel from the 4th century BCE that used similar construction methods, shows mortise and tenon joints spaced approximately every 12 centimeters. Each joint was secured with wooden pegs driven from both inside and outside the hull. The precision of these ancient joints often exceeds what modern craftsmen achieve with power tools. The construction process began with the keel, the ship's backbone. Roman shipwrights selected the straightest, strongest timber available, typically oak for larger vessels or pine for smaller craft. The keel wasn't merely a timber laid on blocks. It incorporated complex joinery at both ends to accept the stem and stern post. These critical joints, which bore enormous stress when the ship flexed in heavy seas, showcase Roman engineering at its finest. After laying the keel, shipwrights attached the garboard strakes, the first planks on either side of the keel. These critical planks established the hull's shape and bore tremendous stress where they joined the keel. Roman builders used especially dense wood for garboards and spaced their mortise and tenon joints more closely here than elsewhere on the hull. Some archaeological examples show joints every 6 centimetres in the garboard strakes compared to 12 centimetres, spacing in upper planks. Building up from the garboards, workers added strakes, rows of planks, one at a time. Each new plank had to be shaped to match the emerging hull form while maintaining proper joint alignment with previously installed planks. This required extraordinary skill, as shipwrights worked without drawn plans, relying on traditional knowledge and their eye for fair curves. They used temporary props and shores to support the emerging shell, but the hull's strength came from the joined planks, not external supports. The shell-first method created several engineering advantages that modern naval architects are only beginning to fully appreciate. First, the continuous wood grain running fore and aft provided exceptional longitudinal strength. Unlike frame-first construction, where planks are cut to fit between frames, shell-first planking could use longer timbers with uninterrupted grain. This made Roman ships incredibly resistant to hogging and sagging, the tendency of wooden ships to bend upward in the middle or droop at the ends. Second, the flexibility inherent in edge-joined planking allowed Roman ships to work in heavy seas without breaking apart. Where rigid modern construction transmits shock loads throughout the structure, potentially causing catastrophic failure, Roman hulls could flex and twist, distributing forces across thousands of joints. Each tiny movement absorbed energy that might otherwise split planks or snap frames. It's similar to how a woven basket can be twisted and compressed, while a rigid box would shatter. Third, the shell-first method created watertight hulls almost automatically. The precision-fit joints, swelled tight by seawater, needed minimal caulking. Many Roman wrecks show remarkably little evidence of caulking material between planks, suggesting the joinery alone provided adequate watertightness. This contrasts sharply with frame-first construction, where planks meeting at frames create numerous potential leak points requiring extensive caulking. The self-supporting nature of shell-first construction offered practical advantages during building. The emerging hull could support its own weight without extensive scaffolding. Workers could actually stand inside the partial hull while fitting new planks, using the completed portion as a stable platform. This reduced construction time and allowed work to proceed even in adverse weather, as the partial hull provided its own shelter. Roman innovations in shell-first construction went beyond mere adoption of Greek techniques. They standardized construction methods across their empire, enabling mass production of vessels for both commercial and military purposes. Roman shipyards developed specialized tools and techniques that increased production speed without sacrificing quality. They created modular designs where certain components, particularly joints and fasteners, were standardized across different ship types. The archaeological record provides stunning examples of Roman shell-first construction. The Mahdia wreck, discovered off Tunisia, dates to around 80 BCE and carried a cargo of Greek art destined for Rome. The surviving hull sections show mortise and tenon joints of exceptional quality, with some tenons still tightly fitted after 2 millennia underwater. Wood analysis reveals that builders selected specific trees for different hull components, matching wood properties to structural requirements. The Uluburan shipwreck, though predating the Roman period, illuminates the deep history of shell-first construction that Romans inherited and refined. This Bronze Age vessel, wrecked around 1300 BCE off Turkey, already showed sophisticated mortise and tenon joinery. By Roman times, this ancient technique had evolved into a highly refined system capable of producing everything from small fishing boats to massive grain carriers. Perhaps the most impressive Roman wreck is the Antikythera ship, famous for its mechanical device, but equally important for its hull construction. Dating to around 70 BCE, this large merchantman shows typical Roman refinements to shell-first building. The mortise and tenon joints are more standardized than earlier Greek examples, suggesting production line manufacturing of components. Tool marks indicate specialized implements designed specifically for cutting these joints quickly and accurately. Roman shipbuilders adapted their techniques for different vessel types. Military ships like the Liburna, a fast, maneuverable warship, used closer joint spacing and denser wood to withstand ramming impacts. The famous Roman trireme, despite its size and complexity, was built shell first with exceptional attention to weight distribution. Every plank was shaped to minimize weight while maximizing strength, allowing these warships to achieve remarkable speeds under oar power. Merchant vessels presented different challenges. The naves, honoraria, large cargo carriers, needed vast internal capacity while maintaining structural integrity. Roman builders achieved this by using wider plank spacing in less critical areas while reinforcing high-stress zones with additional joints. Some merchant vessels exceeded 1,200 tons burden, rivaling wooden cargo ships built well into the modern era. Yet, they achieved this size using only edge-joined planking and minimal internal framing. Rivercraft required different adaptations. Operating in shallow water with frequent groundings, riverboats needed flat bottoms and exceptional bottom strength. Roman builders responded by using thicker bottom planking with closely spaced joints, creating what amounted to a wooden pavement capable of sliding over riverbeds without damage. The Zwammerdam boats found in the Netherlands show these adaptations perfectly, with bottom planking twice as thick as side planking. Fishing vessels represented the small end of Roman shipbuilding, yet even these humble craft showed sophisticated construction. Coastal fishing boats needed to be light enough for beach launching, yet strong enough for daily use in all weather. Roman builders achieved this by using lighter wood, often pine instead of oak, while maintaining the essential mortise and tenon structure. Some fishing boats show simplified joinery, with wider joint spacing but never abandoning the fundamental shell-first principle. The social and economic structure supporting Roman shipbuilding reveals a complex industry. Shipbuilding guilds, collegia, controlled technical knowledge and training. These organizations, part trade union and part technical college, maintained construction standards across the empire. Guild members progressed through apprenticeships lasting years, learning not just technical skills but the accumulated wisdom of centuries of Mediterranean shipbuilding. Master shipwrights held high social status, particularly those building military vessels. Their names appear on inscriptions and contracts, indicating recognition as skilled professionals rather than mere craftsmen. Some achieved considerable wealth, owning multiple shipyards and employing hundreds of workers. The most successful formed dynasties, passing technical knowledge and business connections through generations. The apprenticeship system preserved and transmitted technical knowledge without written manuals. Young men, and they were exclusively men in Roman society, began as simple labourers, gradually learning to cut basic joints under supervision. Years of practice developed the hand-eye coordination needed to cut precise mortises with hand tools. Only after mastering joinery did apprentices learn the more complex arts of plank shaping and hull design. Specialization within shipyards reached remarkable levels. Some workers cut only mortises, developing speed and precision through repetition. Others specialized in shaping tenons, while elite craftsmen handled the complex joinery at stem and stern. This division of labor allowed Roman shipyards to achieve production speeds that seem impossible for hand construction. Records suggest military shipyards could produce a complete warship in under 40 days. The economic impact of Roman shipbuilding extended throughout the Mediterranean economy. Timber requirements drove logging operations from Lebanon to Germany. The demand for quality shipbuilding wood, particularly naturally curved timbers for frames, created specialized forestry practices. Romans actually cultivated trees to grow in specific shapes, bending saplings to create grown frames decades later. This long-term forest management shows remarkable economic planning. Tool manufacturing for shipbuilding became a significant industry. Roman shipwrights used specialized saws, chisels, augers, and drills designed specifically for joinery work. The metallurgy required to create tools capable of cutting precise mortises in hard oak pushed Roman ironworking technology forward. Some Roman shipwright tools show sophisticated features like adjustable depth stops and measurement scales cast into the metal. The supply chain supporting shipbuilding included rope makers, sail weavers, bronze casters for fittings, and lead workers for sheathing. Each component industry developed alongside shipbuilding, creating economic clusters around major ports. Ostia, Portus, Alexandria, and other shipbuilding centers became industrial complexes employing thousands in related trades. The economic multiplier effect of shipbuilding significantly impacted regional economies. Trade in shipbuilding knowledge itself became economically important. Roman shipwrights commanded premium wages throughout the Mediterranean. Cities competed to attract master builders by offering citizenship, tax exemptions, and land grants. Technical knowledge flowed along trade routes, spreading Roman innovations while incorporating local traditions. This technical exchange enriched Roman practice while spreading standardized methods throughout the empire. The military advantages of shell-first construction deserve special emphasis. Roman warships needed to withstand not just weather, but combat damage. The distributed strength of edge-joined planking meant that ramming attacks, unless perfectly placed, often failed to cause catastrophic damage. Where frame-first ships might split apart from a ram strike between frames, Roman ships could absorb impacts across multiple joints, limiting damage to localized areas. Repair capabilities gave Roman fleets significant strategic advantages. Shell-first vessels could be repaired by replacing individual planks without dismantling large hull sections. Military expeditions carried pre-cut planks and skilled shipwrights, enabling fleet repairs in forward bases. This maintainability extended Roman naval reach, allowing sustained operations far from home ports. The ability to repair battle damage quickly often determined campaign outcomes. The psychological impact of Roman naval construction shouldn't be underestimated. Enemy forces facing Roman fleets knew they confronted not just superior numbers, but superior technology. The sight of Roman quinqueremes, massive warships built with the same meticulous joinery as merchant vessels, projected technological dominance. This reputation for superior shipbuilding became itself a tool of Roman power projection. Naval innovations driven by combat experience fed back into civilian shipbuilding. Reinforced ram attachments developed for warships found application in strengthening merchant vessel bows for ice navigation. Waterproofing techniques developed to keep warships operational inspired improved merchant vessel coatings. The cross-fertilization between military and civilian shipbuilding accelerated technical development in both sectors. The gradual transition from shell-first to frame-first construction marks a crucial turning point in maritime history. This change didn't happen overnight. Shell-first building persisted well into the Byzantine period. Economic pressures, changing timber resources, and evolving ship designs gradually favored frame-first methods. The need for larger vessels with greater cargo capacity strained the limitations of edge-joined construction. Frame-first construction offered certain advantages that eventually proved decisive. Larger ships could be built more quickly when frames predetermined hull shape. Less skilled labor could attach planking to predetermined frames versus shaping planks to create fair curves. Timber usage was more efficient when planks could be cut from smaller trees, rather than requiring long, clear lengths for edge joining. These economic factors gradually outweighed shell-first structural advantages. Yet the transition wasn't uniform across the Mediterranean. Small craft in traditional fishing communities maintained shell-first methods into the medieval period. Some regions, particularly the eastern Mediterranean, preserved these techniques longer than others. Islamic shipbuilders inherited Roman methods and maintained them in modified form. The dhows of the Indian Ocean show influences from Roman shell-first techniques spread by trade connections. The legacy of Roman shipbuilding extends beyond historical curiosity. Modern naval architects studying ancient wrecks have gained new appreciation for shell-first construction's sophisticated engineering. Computer modeling reveals that Roman hulls achieved strength-to-weight ratios competitive with modern designs. The principle of monocoque construction, where the skin carries structural loads, pioneered by Roman shipbuilders, appears in modern aircraft and racing yacht design. Experimental archaeology has validated Roman techniques through practical reconstruction. The Carina II project built a full-scale replica using authentic methods, proving that ancient techniques produce seaworthy vessels. These experiments revealed subtleties not apparent from archaeological remains. How the hull flexes under sail, how joints work in seaways, how Roman sailors likely handled their vessels. Such projects bridge the gap between theoretical knowledge and practical understanding. Modern wooden boat builders increasingly incorporate Roman techniques into contemporary construction. The proven longevity of mortise and tenon joints attracts builders seeking durable construction. Some luxury yacht builders now offer Roman-inspired construction using modern tools to create traditional joints. This revival, while niche, demonstrates the enduring value of Roman innovations. The premium prices such vessels command suggest market appreciation for time-tested quality. Environmental considerations give Roman techniques new relevance. Shell-first construction uses wood more efficiently than frame-first methods, reducing waste. The longevity of properly built, edge-joined hulls means less frequent replacement, reducing resource consumption over time. As sustainability becomes increasingly important, Roman methods offer lessons in building durable goods that last generations rather than decades. The cultural impact of Roman shipbuilding shaped Mediterranean civilization. The reliability of Roman-built vessels facilitated trade networks that bound the empire together. Standard construction methods meant ships could be repaired anywhere, encouraging long-distance trade. The confidence inspired by superior shipbuilding encouraged maritime ventures that might otherwise seem too risky. Roman ships didn't just carry cargo, they carried ideas, technologies, and cultural practices that shaped Western civilization. Archaeological discoveries continue to refine our understanding of Roman techniques. Each newly discovered wreck provides data about construction variations, timber selection, and joinery details. Advanced imaging technologies reveal construction details invisible to earlier researchers. Isotope analysis of timber identifies wood sources, mapping ancient trade networks. DNA analysis promises to identify specific tree species and potentially match planks from the same tree across different wrecks. The preservation of shipbuilding knowledge through medieval manuscripts provides crucial links between ancient and modern understanding. Byzantine technical manuals preserved Roman terminology and some construction details. Islamic scholars translated and expanded Roman technical knowledge. Medieval European shipbuilders, though using different methods, maintained vocabulary derived from Roman practice. This linguistic continuity helps modern scholars interpret archaeological evidence. Computer modeling now allows virtual reconstruction of Roman ships from fragmentary remains. By digitally assembling recovered pieces, researchers can extrapolate complete hull forms. Finite element analysis reveals stress distributions in ancient hulls, confirming the effectiveness of Roman engineering. Virtual reality reconstructions allow modern observers to experience Roman ships as their builders intended, walking virtual decks and examining construction details impossible to see in museum displays. Materials science contributes new insights into Roman success. Analysis of ancient wood reveals that Romans selected specific trees not just for size, but for grain orientation and growth conditions. Slow-growth oak from mountainous regions provided dense, strong timber for critical components. Fast-growth pine from river valleys offered flexibility for planking. This sophisticated understanding of wood properties parallels modern engineered lumber selection. The study of tool marks on ancient timbers reveals technological details. Microscopic analysis shows that Roman saws achieved remarkably smooth cuts, reducing joint preparation time. Chisel marks indicate standardized tool sizes across different shipyards. Drill holes show consistent diameter and depth, suggesting standardized bits. These details paint a picture of a mature industry with standardized tools and techniques maintained across vast distances. Economic historians use shipbuilding evidence to model Roman trade networks. The distribution of shipwrecks indicates trade routes and volumes. Cargo analysis reveals commodity flows. Ship sizes suggest economic scales. This maritime archaeological evidence provides hard data for understanding ancient economies. Roman shipbuilding wasn't just a technical achievement, but an economic enabler that made large-scale trade profitable. Climate researchers extract environmental data from ship timbers. Tree ring analysis reveals rainfall patterns during growth years. Isotope ratios indicate temperature variations. This climate data, precisely dated by archaeological context, helps reconstruct ancient Mediterranean weather patterns. Roman ships thus provide unexpected windows into environmental history. their timbers preserving climate records spanning centuries. The question of why Romans abandoned such successful techniques puzzles historians. Simple economic explanations seem insufficient, given shell-first construction's proven advantages. Cultural factors likely played a role. Frame-first methods may have seemed more modern or aligned with Northern European traditions as the empire's centre shifted. The loss of accumulated technical knowledge during societal disruptions certainly contributed. Like many technological transitions, multiple factors probably combined to end a 1,000-year tradition. Lessons from Roman shipbuilding apply beyond maritime contexts. The principle of distributed strength through multiple small connections appears in modern engineering, from composite materials to network design. The concept of building self-supporting structures that gain strength through assembly parallels, modern space frame construction. Roman builders intuited principles that modern engineers express mathematically, but achieve similar results. The social organization of Roman shipbuilding offers models for modern technical industries. The guild system's combination of quality control, knowledge preservation, and skills training address challenges still facing technical trades. The progression from apprentice to master through demonstrated competence rather than formal education parallels modern certification programs. Roman solutions to organizing complex technical work remain relevant. Environmental sustainability lessons emerge from studying Roman practice. Building for centuries rather than decades reduced resource consumption per year of service. Using locally available materials minimized transportation costs and emissions. Designing for repair rather than replacement extended vessel life. These principles, forced by ancient technological constraints, offer voluntary choices for modern sustainable design. The aesthetic legacy of Roman shipbuilding influenced Western design traditions. The fair curves of edge-joined hulls, determined by wood's natural bending properties, created forms of enduring beauty. These shapes, refined over millennia, achieve hydrodynamic efficiency through evolution rather than calculation. Modern yacht designers still study Roman hull forms for inspiration, finding that ancient proportions often match computer-optimized shapes. Cultural memory preserves Roman shipbuilding's impact through language and tradition. Terms like shipshape derive from the high standards Roman builders maintained. The concept of a tight ship references the precision joinery that made caulking nearly unnecessary. Maritime traditions worldwide show Roman influence spread through centuries of cultural transmission. Even cultures that never directly encountered Romans inherited practices spread through maritime networks. Modern Italy maintains connections to Roman shipbuilding traditions through small boat construction in traditional communities. Fishermen in certain regions still prefer edge-joined construction for specific boat types. These communities preserve not just techniques but the cultural context, the songs, stories, and rituals surrounding traditional building. This living heritage provides insights into ancient practice that archaeology alone cannot recover. The philosophical implications of Roman shipbuilding challenge modern assumptions about technological progress. Romans achieved remarkable results through patient refinement of traditional techniques rather than revolutionary innovation. Their willingness to invest enormous labor in precise joinery contrasts with modern preferences for quick assembly. This different relationship with time and craftsmanship offers alternative models for contemporary making. Educational programs increasingly incorporate Roman techniques into curriculum. Maritime archaeology programs teach students to recognize construction details. Wooden boat-building schools offer courses in traditional joinery. History of technology courses use Roman shipbuilding as case studies in engineering evolution. This educational transmission ensures that knowledge of Roman techniques spreads beyond specialist communities. Museum exhibitions bring Roman shipbuilding to public attention through innovative displays. Full-scale reconstructions allow visitors to appreciate ancient vessels' size and complexity. Cutaway models reveal hidden joinery. Interactive displays let visitors try virtual joint assembly. These exhibitions transform archaeological knowledge into public understanding, building appreciation for ancient achievement. Popular culture occasionally references Roman shipbuilding, though rarely accurately. Films depicting ancient naval battles seldom show authentic construction details. Historical novels occasionally mention building techniques but rarely make them central. Video games increasingly include realistic ship models based on archaeological evidence. This popular exposure, however imperfect, maintains public awareness of Roman maritime achievement. The future of Roman shipbuilding studies looks promising as new technologies enable deeper investigation. Underwater robots can explore wrecks too deep for divers. Advanced imaging penetrates concretions, hiding construction details. Machine learning identifies patterns in joint placement across multiple wrecks. These technological advances promise continued revelations about ancient techniques. International collaboration accelerates discovery and interpretation. Mediterranean countries share archaeological data through digital networks. Standardized recording protocols enable comparative analysis. Joint expeditions pool expertise and resources. This collaborative approach mirrors the international nature of ancient Mediterranean shipbuilding, where techniques spread freely across cultural boundaries. Climate change impacts on underwater archaeological sites add urgency to shipwreck studies. Rising sea temperatures accelerate wood deterioration. Changing currents expose previously protected wrecks. Coastal development threatens nearshore sites. This race against time motivates intensive documentation efforts to preserve knowledge before sites degrade beyond study. The relevance of Roman shipbuilding extends into humanity's future. As we contemplate expansion beyond Earth, principles of efficient construction using limited resources become critical. Roman builders' ability to create strong, durable structures with simple tools and local materials offers models for space construction. The mortise and tenon joint's mechanical simplicity suits environments where complex fasteners might fail. Biomimetic engineering finds inspiration in Roman techniques. Just as Roman joints mimicked natural wood connections, modern engineers seek biological models for strong, flexible connections. The distributed strength of shell-first construction parallels biological structures from plant stems to animal bones. Roman builders intuited principles that modern science confirms through different paths. The democratic aspects of Roman technology deserve emphasis. Unlike monuments built for elite glory, ships served practical transportation needs. Their construction employed thousands of ordinary workers, whose skills created extraordinary vessels. This marriage of common labour and sophisticated engineering characterizes the best of Roman achievement. Ships embodied Roman values of practical accomplishment serving collective needs. As we conclude this exploration of Roman shell-first shipbuilding, several themes deserve emphasis. First, Roman builders achieved remarkable results through patient refinement of inherited techniques. They didn't revolutionize shipbuilding but perfected it through countless small improvements. This evolutionary approach created vessels of extraordinary capability that served Mediterranean needs for over a millennium. Second, the integration of technical, social, and economic factors created a total system greater than its parts. Roman shipbuilding succeeded not just through superior joinery, but through supporting institutions, guilds, shipyards, supply chains, and training systems. This holistic approach to technology development offers lessons for modern innovation. Technical excellence alone doesn't ensure success without supporting infrastructure. Third, Roman methods achieved sustainability through durability. Building vessels to last centuries rather than decades represented ultimate resource efficiency. Modern throwaway culture could learn from Roman commitment to quality construction. The extra effort invested in precise joinery paid dividends through extended service life. Short-term efficiency often proves false economy compared to long-term durability. Fourth, the loss of Roman techniques reminds us that technological progress isn't inevitable or irreversible. Superior methods can disappear when supporting knowledge systems fail. Preserving technical knowledge requires active effort across generations. Roman shipbuilding's disappearance warns against assuming that useful technologies automatically persist. Cultural continuity matters as much as technical merit. Finally, studying Roman shipbuilding enriches our understanding of human achievement. These ancient builders solved complex problems with elegant solutions that modern technology struggles to match. Their success encourages humility about modern superiority while inspiring admiration for human ingenuity across ages. Roman ships sailing Mediterranean waters carried more than cargo. They embodied centuries of accumulated wisdom shaped into wood. The story of Roman shell-first shipbuilding ultimately transcends maritime history. It demonstrates how patient craftsmanship, systematic organization, and respect for inherited wisdom can create technologies of enduring value. In an age of rapid obsolescence and disposable goods, Roman commitment to building for the ages offers alternative values worth considering. As you complete this journey through Roman shipyards and across ancient seas, consider how modern life might benefit from Roman approaches. What current technologies might improve through patient refinement rather than constant revolution? How might building for centuries rather than years change design priorities? What wisdom might we preserve more carefully for future generations? The Roman ships that once crossed the Mediterranean have long since returned to earth and water, yet their construction principles remain sound, their engineering valid, their lessons applicable. In understanding how Romans built ships backwards from modern methods yet achieved superior results, we gain perspective on assumptions about progress and efficiency. Sometimes the old ways, refined through generations of practice, surpass quick modern solutions. Whether we marvel at precise mortise and tenon joints in ancient wrecks or appreciate the social systems that created them, Roman shipbuilding deserves recognition as one of humanity's great technical achievements. It reminds us that technology serves human needs best when it combines innovation with tradition, efficiency with durability, individual skill with collective organization. The Roman shipwright fitting planks edge to edge created more than vessels. He built connections across time that still inform and inspire.